So test the leg, everybody. So today I'm going to do last part of this chapter. So last time we talked about atoms. We talked about the different models of atoms, and we talk about a few models, right? Like Bohr model, like J.J. Thomson models, and Rutherford models, and Bohr models. And when we talk about the Rutherford models, we talk about nucleus. Rutherford discovered a nucleus, and he says that electron is going around nucleus. However, a Rutherford model is very classical, so he was not able to explain so many phenomena observed from atoms, such as different spectral lines. So in a way, so many observation has been done much before Rutherford. His model was not able to explain those observations, right? Such as spectrums, emission spectrums we talked about last time, right? And then we talk about Bohr model. Last class we talk about Bohr models. When we talk about Bohr model, we say that Bohr model consists of three postulates, and with those three postulates, we would able to explain so many aspects of so many parts of observations, that is spectral lines and all, and he was able to relate between the structure of atoms and the spectral line observed, right? So this is what we have. And then last time we talked about the three postulates, and we said that the first postulate is all about orbit, and that is he talks about a stable orbit and what we call as non-radiating orbits. Unlike classical electromagnetism, right? He says that when electron goes around in that orbits, electron doesn't emit electromagnetic radiation, and this is what we call as non-radiating orbits. And now the second part is what kind of condition should satisfy it. All right, that particular orbit must satisfy it. So he says that this is very puzzling, postulates. That particular postulate, that particular orbit should have an angular momentum integral multiple of h by 2 pi. H is a Planck constant, and he said this is a Planck constant. So he said that the electron can take only those orbits where the angular momentum is integral multiple of h by 2 pi. All right, and then the third postulate talks about the spectrums, right? How the photons are being released from atoms, right? Why we find different spectral lines. All right, so this is what is. So this is his postulate. He says that yes, there can be line spectra for hydrogen atoms, but due to the line spectra of hydrogen atoms are due to transition of electron from higher energy level to lower energy level. That when the electron jump from higher energy level to lower energy level, electron emits the photons, and such that the frequency of photon is given by these equations, right? EI is initial energy, and which is more than final energy. All right, so this is what we have, and mu is the frequency, h is the Planck constant. So this is what we talk about. So in a way, the photons are released from an atom is all due to electron transitions, electron undergoing transition from higher energy level to lower energy. That's the point. And then we talk about electron going around nucleus, and when electron goes around nucleus, we talk about angular momentums. Whenever we talk about angular momentum, it is represented by L. L is given by mv. This is what we talk about angular momentums. M is mass of electrons, and V is velocity, and R is radius. All right. So now, if I say if electron is going around n orbits, he talks about different orbits. When electron is going around n orbits, he says that angular momentum for n orbit must be equal to V n R. This is what he talks about. Now the purpose of doing this is to understand, to derive we talk about different orbits. So what about energy for each orbit? Alright, so we are going to derive energy, right? We are going to derive energy of an electrons at particular orbit, and we also try to get the radius of an orbit. So this is what we have. And he says that the both second postulates say that is, let's say a second postulate. The second postulate says that this angular momentum of an n orbit is n times h by 2 pi. Alright, this is his postulate. And having this, now I can say that this is equal to mv and rn must be written as nh divided by 2 pi, and rn can be written as nh divided by 2 pi mvn. This is the orbit. This is the radius of an orbit. This is the radius of an orbit. Alright, so I'll just put star, right? I'll just put star. Alright, now this is what we have. Now again, when we talk about electron, I told you the Bohr model is semi-quantum mechanics. So he also includes the classical idea also, that is Rutherford ideas, that is electron going around nucleus. So having a Rutherford models, I just take a Rutherford models. From Rutherford model, let's say a Rutherford models. Let's say a Rutherford model says that electron going around nucleus. So that electron going around nucleus, that is a centripetal force. Centripetal force is equal to electrostatic force. And having this, I can say that Vn equal to E square divided by 4 pi epsilon naught Rn. So this is what we have, and I can say that Vn can be written as square 4 pi epsilon naught mRn. Having this. Now what I'm going to do is I will just substitute the value of Rn, right? I will just substitute the value of Rn. So Vn square, I'm sorry, this is m. This m puts here, Vn square is equal to E square divided by 4 pi epsilon naught Rn, and having the value of substituting the value of Rn. If I substitute the value of Rn, what we get is E square divided by 4 pi epsilon naught. What is value of Rn, right? Value of Rn is nh divided by 2 pi m or Vn. Alright, so this goes up and this goes up. 4 pi epsilon naught, then n, I'll just say n at this point, 1 by n, alright, h by 2 pi m dot Vn. Alright, so this m cancel out with this m, and v cancel out with this v. Finally I get a value. Vn value is equal to 1 by n E square divided by 4 pi epsilon naught 4 pi epsilon naught h by 2 pi. So this is the value of Vn. This is the value of Vn. Now what I'm going to do is that I will substitute the value of, I'll take the value of Rn. Let's take the value of Rn. Take Rn is equal to, I'll take this nh divided by 2 pi m what is the value of Vn? I take the value of, substitute the value of Vn. Vn is equal to E square divided by 1 by n 4 pi epsilon naught h by 2 pi. Alright, so having this value, I will just do some simplifications, and n goes up, I just say n square, and here I have an m, alright, and then h 2 pi, h, alright, so 2 pi, alright, h divided by 2 pi whole square, h1, h2, h square, 2 pi square. Then this 4 pi goes up, and then epsilon naught divided by E square. So this is the value of Rn. This is the value of Rn. So now I'll write it here. Value of Rn is equal to n square divided by m, and then h divided by 2 pi whole squares and 4 pi epsilon naught E square. So this is the value of Rn. All right. So that means, as this implies that as you increase the number of orbit, radius goes on increasing, right? Radius goes on increasing. Now what I'm going to do is, I just substitute the value of all are constant, right? These all are constants. Everything is constant. M is the mass of electrons, everything is constant. So now if I put n is equal to 1s, if I say if n is equal to 1s, then R1 is equal to h square pi epsilon naught pi m d square. And I say this could be a smallest orbit, so therefore I would like to represent this by a naught, which is equal to h square epsilon naught pi m d square. So this is what we call, and this is what when we substitute the value of h epsilon naught pi m e squares, the value comes around a naught. Value of a naught comes around 5.29 into 10 raised to the power minus 10 meter. This is the radius of hydrogen atoms, right? This is the radius of hydrogen atoms, and this is what we call as a Bohr radius. This is what we call as a Bohr radius. This is what we call as Bohr radius. This is what we call as Bohr radius. All right. This is what we call as Bohr radius, and this is going to be a smallest radius. This is going to be a smallest radius. All right. Now again, I would like to take that. I would like to take that energy of an atoms in case of when we use these Rutherford models. We say that this is going to be E is equal to minus E square divided by 8 pi epsilon naught Rn. This is the energy. Alright, this is the energy of electron. This is the energy of electron having a radius Rn, right? Energy of electron having radius Rn. This is the energy of an electron having radius Rn. Now I would like to substitute the value of Rn's. When I substitute the value of Rn's, Rn, what is the value of Rn? This is the value of Rn. Alright, this is equal to n square divided by m Alright, h by 2 pi, okay, 4 pi epsilon naught e square, right? So this all reciprocals. So finally what I'm going to get is minus e square divided by 8 pi epsilon naught m by n whole square. This is going to reciprocal, right? When it's reciprocal, I'm going to get m divided by n square. And this is going to reciprocal. When this is going to reciprocal, I say the 2 pi divided by h whole square. When this is going to reciprocal, h and 2 pi goes up and h is set down. And this is going to reciprocal, I get e square divided by 4 pi epsilon naught. Okay, and now I just simplify this. When I simplify this, finally what I'm going to get is, when I simplify this, finally I'm going to get minus me4 minus me4 8 n square epsilon naught square h square, right? Or I write here this is equal to minus 1 by n square and me4 divided by 8 epsilon naught square h square, right? So now if I substitute the value of all this, right? If I substitute the value of epsilon naught h square, finally what I'm going to get is this equal to minus 2.18 into 10 raised to power minus 18 divided by n square joule. This is the value we are going to get. This is the energy of an orbit. This is the energy of an orbit, right? Energy of electron occupying an orbit. This is the energy of electron occupying an orbit. So now, if I convert a joule into electron volt, all right. So 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joules. And then when I convert this into electron volt, we will get a value that is, this is equal to minus 13.6 divided by m squares electron volt. So this is the final result. So this is going to be a final result. So energy of an orbit is going to be 13.6 electron volt divided by n square. This is the energy in terms of electron volt. This is the energy. N is the energy level, right? N is the orbit. I can say n is the orbit, number of orbit. First orbit so for first orbit, when n is equal to 1, then this value comes in E1 is going to be minus 13.6 electron volt, and the minus indicates that electrons are bound to nucleus. So now as I go on increasing, and the value goes on decreasing, that means energy is increasing. That means excited. They are in excited states. So therefore, this is the ground state. This is the energy of electron at a ground state, right? Energy of electrons at ground state. All right, that is the first orbit. All right. So having this, now we found this. This is expression. Now we can easily find out the energy at second energy level, third energy level. We can find out energy of first orbit is done. second orbit we can substitute the value of this, right? It goes on like that. All right, so this is what we are going to do. So this is the energy level, right? Having this right now, I just write here this expression, very important expression, minus 13.6 electron volt and square, right? So now first orbit, this is the ground state. This is the ground state. So for now, now I can get different energy levels for an atom, right? For an atom, right? For n is equal to 1, that is ground state, at electron at ground state, electron at ground state, and the value found to be 13.6 electron volt. Now electron can occupy only this, alright? These all are, electron can't take and take any kinds of an orbit, right? Electron can take all those orbits, these kinds of orbit, right? Electron can not take arbitrary orbits, right? Random orbit. Electron has to take a specific orbit, that is non-radiating orbit, right? So the first excited state, n is equal to 2, that is the first excited state. First excited state, that is, I'm sorry, this is 1, right? This is 1, 2 to the 4, value comes around minus 3.40 electron volt. This is the first excited state. Now second excited state, state's value comes around. Now as you go higher and higher, energy goes on increasing, right? Energy goes on increasing. This is 9, value comes around minus 1.51 electron volt. Now fourth excited state, third. Now n is equal to 4, that is, I'm sorry, right? This is 4th, that is the third excited state. This is the fourth orbit. This is the fourth. Ground, first, second, third, right? This value comes around 16, which is equal to minus 0.85 electron volt. So those are right. So this is the first excited state, second excited state, third excited state, fourth excited state, right? And as number goes to a very high, and these are what we call as unbound, that is ionized, right? So how much energy is required to ionize a hydrogen atom, right? So that means you have to supply this much amount of energy, right? If you supply 13.6 electron volt, all right, and then electron can be excited, electron can be kicked out from hydrogen atom. So this is what we call as ionization energy. What is ionization energy? Ionization energy is the energy required to remove electron from hydrogen atom or whatever atom you are going to choose, right? So therefore with this at a ground state, with this energy, electrons are bound to nucleus, right? If I supply this much amount of energy, electron can be removed from hydrogen atom or whatever atom may be, right? At this point, this is going to be hydrogen atom, right? So this is the different energy level of an hydrogen atom, all right? Now I would like to do line spectra. That is the observation done by Blumer and all, right? So this is what we talk about. Observation done during a large late or 19th century, right? So this is what we have. So first let's talk about both third postulates. The spectral lines are because of both third postulates. Spectral lines, the formation of spectral lines are answered by both third postulates. So third postulate, when I say that this is alright, so initial energy levels are higher than final energy level, right? So is less than, this is what we have done last time, right? So now look at here. Now this is this part. What we are trying to understand is we would predict, right? The Bohr model would able to predict what kind of spectral lines can be formed, right? So this is what we have, and this was observed much before, all right? And Bohr theoretically tried to prove those things, right? So this is what we have. The frequency of photon that is equal to, this is the frequency of photons. This is the frequency of photons released when electron undergoing transition from the initial energy level to the final energy levels. So that is equal to alright. So what we would like to do is how much is this value? This value comes around NE square divided by NI square. This is going to be minus, alright, 8 epsilon naught square H square. This value is 4. I'm sorry. And minus ME4 divided by NF square, 8 epsilon naught square H square. This is what we have. Now I substitute the value. When I substitute the value, minus into minus is plus, and all others are constants, the same. So 8 epsilon naught square H squares 1 by NF square minus 1 by NI square. So this is the what we have, right? Square, right? This is what we have done, right? So this is what we have. Finally, this is the. And now I just say frequencies are given by H2. Alright, so electron undergoing a transition from higher energy level to lower energy level, right? And due to which photons are released with this much frequency. And this is just a theoretical work, right? This is not experimental done. And experimentally it was done far, was done much before, like in year 1890 something. That the first was done by Blummer, right? So this was the observations. Now, if I use wavelength, we know that C is equal to H lambda mu, that we all knew, and therefore mu is equal to C by lambda. All right. Therefore, so 1 by lambda is going to be ME4 8 epsilon naught E H cube C, alright, and then 1 by NF square minus 1 by NI square. So this is the value. And look at here, the interesting part is that this was already empirically it was done by a Blummer, right? It was done by a Blummer. And when Blummer did this, he said this is Ribot constants. 1 by nf square minus 1 by ni square, right? The value found by the theoretical value found by a bow comes around, value comes 10 raised to power minus 10 raised to power 7 per meter. This was the value found by a bow. Theoretically it was found. This is what we call as a Rydberg constant. The theoretical value of a Rydberg constant found by a bow is this, right? And experimentally it was found by a Blummer, that is the value of experimental value is 0.97 into 10 raised to power 7. This was experimentally obtained from a Blummer empirical formula, right? Empirical formula, right? So now look at here, this is the theoretical value and this is the experimental value, and values are very close, which implies that the Bohr model is right. Bohr postulates are right. Which implies that the Bohr postulates are right. So this is what we talk about, right? And having this, now we would able to define the spectral lines. We would able to define, theoretically we would able to define the difference, empirical formula, right? Defined by Blummer, right? So this is what we have. So he says that, therefore I say these are the spectral lines. Any electrons occupying higher energy levels comes down to a ground state. This is what we call as a Lemon series, right? So Lemon series is defined as the spectral lines. Electron undergoing transition from higher energy level to ground state is what we call as a Lemon series. This is what we call as a Lemon series, right? So therefore, for Lemon series, what we found is this is equal to 1 square minus n square, right? Where n is equal to 2, 3, 4, go on. This is for Lemon series. Now this is for Lemon series. Now for Blummer series, this is the ultraviolet range, right? For a Blummer series, we say that any electrons which undergo a transition from higher energy level to first excited state, higher energy level to first excited. This is a first excited state, right? This is from higher energy level to first excited state. So this is the Blummer series, right? Electron, this is the Lemon series, and this is the Blummer series. And now electron undergoing electron coming from higher energy level to this, electron coming from higher energy level to this. So this spectral series is what we call as a Blummer series. Now any electron which comes down from higher energy level to a second excited state, is what we call as Paschen series. This is what we call as a Paschen series, right? This is what we call as a Paschen series, right? So this is what we have. This is one set of spectral series, and this comes in an infrared line, right? So now any electron which undergo a transition from high energy level to a fourth excited state, this is the third, right? Third excited state, this is the third excited state, and this is what we call as bracket series. This is what we call as. So on, we would able theoretically Bohr model fits line spectra of hydrogen atoms. Theoretically, Bohr was able to explain the line spectra of hydrogen atom. How and why electron, why hydrogen atom exhibits this fine line spectra. All right, this was explained by Bohr model, right? This is what we talk about spectral lines of a hydrogen atom. Now you know, say whatever things observed, whatever phenomenon observed by those scientists could be explained by, can be explained by a Bohr model, right? So this is what we have, and this is another we have. All right, this is a Lehman series. It's all a Lehman series, and Lehman series has a different frequency, right? If it is coming from much higher energy level, then the frequency must be higher. This is a Blummer series, Lehman series. This is a Blummer series. These are the energy level. These are the energy level, right? These are the energy level, right? And this is a Paschen series, and this is a bracket series. This is a Fund series. So these are the different, and this was observed much before Bohr, right? Maybe 10 years before Bohr actually described or actually explains. All right. Now what we are going to do is we are going to do last part, right? And when we go through a three postulate of a Bohr, right? The most puzzling postulate is the second postulate, and Bohr he himself never knew why electron take this kind of angular momentums. All right, why electron take this kind of angular momentums, right? So electron takes the particular angular moment. This is what we call as angular momentum quantization of angular momentums. All right, and the Bohr, you know, Bohr's model of atom was done in year 1913, and the explanation was done in year 1923. All right, and it was D. Broglie. He put forward the model as particle wave theory, right? Particle wave theory, right? Particle wave theory, right? Particle wave theory. That means any particle that has a momentum has wavelength, right? And this is what we call as de Broglie hypothesis, right? De Broglie hypothesis, right? De Broglie hypothesis, right? And the de Broglie hypothesis was experimentally it was found by two scientists, that is Davison and Germer. This is the experimental setup. Davison and Germer experiments confirmed that yes, electron has wave natures, right? Electron has wave natures, and the wavelength of electrons is exactly what Bohr has, what de Broglie has, found, right? De Broglie found the wavelength of an electron going around nucleus, wavelength of an electron, wavelength of any matters having some momentum, right? This was experimentally found by Davison and Germer. So therefore the de Broglie was awarded Nobel Prize. All right. So this is the Davison-Germer experiment. This is the experimental setup. This is not there in syllabus. This is the electron detector. No, right? And now look at here. Now the most I told you, right? Most puzzling equation is the parts of a Bohr model is second postulate. What is the second postulate? Angular momentums, right? So angular momentum is equal to people never knew why electron take this particular angular momentums. Why electron take this particular angular momentums? All right. So to answer this, we have to consider that when electron going around the nucleus, electron takes a wave natures, right? To answer this, when electron goes around the nucleus, when electron goes around the circular orbits, electron takes wave nature, right? Electron takes wave natures. So what I call as particle waves. Particle wave while electron going around nucleus. What I call as a particle waves. Particle wave. Alright. having this, now we know that electron going around nucleus and electron takes a circular path. Electron take a circular path. Alright, when electron take a circular path, now wave, particular wave, electron wave, a particular wave is confined in a circular path. Confined in a circular path. Having this, now I would like to bring you a concept that is done in a class 11. That is a standing wave concept, right? Standing wave concept. If you allow a wave, if you allow a wave to travel in a strings, if you allow a wave to travel in a strings, and if you pluck a strings, or if you allow a wave to travel in a strings, in that particular strings, what we get is what we call as a standing waves. This particular length of strings allow only few wavelength to exist, right? So this is what we talk about the standing waves, alright? So if I have a strings, if I pluck, alright, initially you find so many waves and all superimpose each other and cancel each other. Finally we get a particular wave, right? We got particular vibrations, and that is what so this is what we call as a standing wave. So let's say, I'll give you an example, right? Maybe could be some kind of recapitulations. These are the two rigid support where strings are being held. Then I plug the strings. When I plug the strings, initially there can be so many waves, and this all wave cancel each other, superpositions, right? And now finally there will be a wave whose wavelength, right? Whose wavelength is integral multiple of strings, right? This is what we call, right? So this is what we have. So this is going to be an anti-knot. This is going to be a knot, right? This is going to be a knot. This is going to be an anti-knot. So this guy, and this is also possible, right? This is also possible. Possibility is that at the two ends this should be knot. All right. So how many waves that is done in our class? What we call as a harmonic, first harmonic, second harmonic, third harmonic. That is done in a class 11, right? This is done in class 11. So likewise, now here, why you get is here the waves are confined. The waves are confined in a particular boundary, right? Between a particular boundary. So that is why you get what we call as a standing wave. Likewise, this is the analogy, right? So this is the analogy for the electron going around nucleus. Now I say that when electron goes around nucleus, all right, electron act as a particle wave. Electron act as a particle waves, and it says that since it is a standing wave, it exists only a resonance, right? This exists only at a resonance, right? So since this is a standing waves, I say this is again I miss one concept. These all are resonant case. These all are resonant case, right? Only that resonant frequencies exist, right? And now since particle waves are confined in a circular paths, and only wavelength that electron particle can exhibit, are I say this is the circumference, that is the path of length of path. Let's say length of path of electrons is equal to n lambda. N lambda means, this could be a 1, alright, this could be a 2 lambda, this could be a 3 lambda, this could be a 4 lambda. So that's the what we talk about, right? It is not that half lambda and 1.5 lambda, something. This is not possible, right? So I said, since the electron takes a wave natures, it is only it exhibits as standing. It is very same as the standing wave, right? Done in class 11, right? So electron can take those wavelengths such that the path length of electron is equal to integral multiple of wavelengths. So if you take a 1 wavelength, you can take a 2 wavelength, you can take a 3 wavelength, so on. So this, and having this, we can easily prove, right? We can derive Bose-Second postulate from this, right? So that is, now I say this is done. So the path length of electrons, right? Path length of an electron must be equal to integral multiple of lambda, right? Integral multiple of lambda, right? So this is what we have, and n is a number of orbit. N is what we call as number of orbit. Okay. So now I take a de Broglie wave hypothesis, right? De Broglie says that this is going to be Hp, and what is P? MVN, right? MVN, right? So now having this, now what about lambda, right? So this is going to be 2 pi Rn n lambda divided by MVN, right? This is what we have. And now it goes this side, MVN Rn must be equal to Ns divided by, this is Ns divided by 2 pi. So this is angular momentum. Look at here, now we get, right? Now we can derive Bose-Second postulate, right? Using de Broglie hypothesis. So this tells that the Bose-Second postulate is a result of a de Broglie hypothesis. That means this can be explained only if electron has wave natures. Now we call it as a particle wave. When electron going around nucleus, alright, electron take the particle wave natures, and electron under resonance, alright, under resonance, electron exists in an orbit. So therefore electron can take this angular momentum, right? So therefore electron cannot take arbitrary orbits, right? So electron can take only some specific orbit, right? This is the reason, right? So this is what we talk about. So therefore a Bohr postulate talks about a discrete orbit and a discrete energy level, right? So therefore I just say Bohr postulate talks about discrete orbits, that is first orbit, second orbit, third orbit, and a discrete energy level, right? Energy level. So this is the Bohr postulates. Alright, so I will give you a few more diagrams of this. So hydrogen atom, electron wave resonance. So that's electron wave resonance. All the orbits are what we call as a wave resonance, right? Only at resonance they exist, right? As we have done in our string wave, in our string waves. This is the first, n is equal to 1. This is when n is equal to 1, and this is n is equal to 2. This is n is equal to 3. Goes on like that. Okay. Now, last we would like to talk about the limitation of Bohr model. Limitation of Bohr model. The Bohr models could everybody explains, let's say 95% of hydrogen atoms, right? Bohr model explain hydrogen atoms, right? Bohr model explain hydrogen atom means the property that hydrogen atom exhibit, that is the line spectra of hydrogen atoms, right? Why? Because Bohr model is involves so many quantum mechanics concept, right? So, however, the Bohr model has some limitations, right? Bohr model is not purely quantum mechanical model, right? So, the few limitations of a Bohr model is that Bohr model is applicable only to a hydrogenic atom. That means atoms having one electrons, atom having one electrons, right? Bohr model, right? Why? Because if an atom is having more than one electrons, Bohr never talks about the electron-electron interactions. Bohr only talks about interaction between a nucleus and electrons. Bohr never mentions the interaction between an electron and electron. So therefore, Bohr model is not sufficient to explain the higher, heavier atoms or atoms which are having more than electron having more than hydrogen atoms, right? And then another limitation of Bohr model is that when you observe spectral lines of hydrogen atoms, some spectral lines are brighter. The intensity of spectral lines, they are relatively variations, right? They are variation of intensity in case of hydrogen atoms, right? So some spectral lines are more, brighter, and some spectral lines are less bright. So Bohr model could able to explain why spectral lines are formed, right? Bohr model could guess that yes, in this particular spectral lines, electron translation is more, right? If there is more electron translation, then the more photon will release, and then the brighter would be. All right. This was able to explain from a Bohr model, but Bohr model could not able to explain why those electron translations are more favorable than others. Why some translations are more favorable, some electron translations are more favorable than another electron translation. So he was not able to explain, right? So therefore, the Bohr model is unable to explain the relative intensity or frequency in the Bohr model exactly predict the frequency of a spectral line, but intensity wise he was not able to explain why some intensities are higher and why some intensities are less, right? So this is the limitation of Bohr model, right? With this we come to the end of chapter atoms. So today I will end this and maybe next week I would like to do nuclei, and nuclei few topics has been deleted, so now we are left with only 2 chapters. Thank you.